Hello guys, welcome back to our course. In this lecture 2, we're gonna start, exploring or reviewing basically, the assembly language that we're gonna use in throughout the course here. So as we mentioned last time, we will adopt in this course MIPS, architecture, processor architecture. There are many architecture like x86, ARM, MIPS. So MIPS is really very good in the sense is that it is really simple. It's not complex. It's basically support a RISC architecture. It's a RISC architecture, so you have a reduced instruction set architecture. Also easy to compare to other, architecture, processor architecture. It's easy to, design in hardware. Actually, the assembly language itself is designed so that the hardware will be easy to implement. That's a very important concept. Okay, so let's start our review. This is basically in chapter 2 of our book. So what is an instruction set? So an instruction set is basically, a group of, instructions or what's called mnemonics, like add, subtract, mul, and many other, instructions or mnemonics like this. So different computers, different architectures has or have different instruction sets. Like for example, Intel and AMD processors usually use instruction set called x86 and other derivatives of this x86. ARM processors, use what's called ARM instruction set. MIPS processors, use MIPS, and there are very similarity, a huge similarity between MIPS and ARM. Both, target RISC architecture process of processors. Both, target, easy and fast design and also power efficient processor designs. So, although many or different computers has different instruction set, still there are many common aspects. Like for example, you're gonna see add instructions in all of them, mul instructions in all of them. Okay, but of course there are also other differences. But the bottom line is, if you know one language, like for example x86, which is very famous, and you probably studied this before, it will be easy for you to understand, other instruction sets for other architectures. It's like MIPS, for example. Early computers had very simple instruction sets, and this is basically because, early computers are very simple, in hardware, the hardware itself is simple, small, cannot do complex stuff. So basically, on the other side, or the flip side of the coin, the instruction set must also be simple, because basically you can do simple operations on such small and simple processors. Also, many modern computers has also simple instruction set, but this is for different reason. So in the past, what hindered us from having big instruction set is that the technology wasn't advanced. So you can, you are short-handed as a designer to implement many cores in your processors, many logic, because the number of transistors, for example, was low that you can implement in a chip or put in a chip. But now, although we have very advanced technology, we still favor, in many designs, simple instruction set. And that's because, for example, the power efficiency. So, for example, your smartphone processors usually, or maybe all of them, use ARM architecture. And why is that? Why is that? Because ARM, the company ARM, basically, when they do or when they invent or introduce their ARM processor with ARM instruction set, their main target was power efficiency because, okay, they say in the market there are many handheld devices or battery operated devices. We want the users to use these, devices like laptops and smartphones as long as possible without recharging the battery. So our design should be power efficient. Power efficient means your design should be simple circuits, compared to other architecture, like for example, Intel processors. So we still favor, to this day, such, or simplicity in instruction sets such that because this will be reflected in the design of the processor to be also simpler. MIPS instruction set. So again, MIPS is used as, example throughout the book. Okay. Still, there are, although it's not very famous in the market to see a processor uses MIPS, but still there are many, applications, especially in embedded applications in the market that use MIPS. Like for example, network or storage equipments, cameras, printers, something like this, stuff like this. And if you want to know more about MIPS, just to go, to appendices here, B and E, to know more about, this instruction set. Okay, so let's now go into an overview about this, instruction set. So as we said, instruction set is basically the language of the compiler. Okay, and you should know that this language, has two forms: a readable form, a human readable form, and original form. The original form is the form that the processor can understand, basically zeros and ones. So the processor understand the processor is a logical circuit. So it understands two kinds of voltages, high voltage, low voltage. High voltage is one, represented with symbol 1. Low voltage is a symbol represented with the voltage 0 or low voltage. Or you can say a charge or not charge. So if you have a memory, for example, ones and zeros there is a little bit different. 1 means you store 1, 0 means you store nothing. So this is, what's called machine code. But if as a human, if we dealt with the machine code, it will be very hard for us to understand. So that there is another form of the instruction set, which is basically the assembly. So the assembly instruction is basically a group of zeros and ones, but written in English, so you can understand it as a human. So what comes to mind when we first introduce ourselves to an instruction set or a computer language is how to do arithmetic operations, like addition, for example. So let's say, you have an example here, add A, B, C. One may say this means we're going to add A plus B plus C. No, that's not the case. So it's basically, something like A equal to B plus C. So this is basically what we do, for example, in C or C++. And this is how we do it in assembly. Okay, so there are two sources and one destination. Source 1, source 2, and destination. The destination is the location at which you're gonna store the value of the addition, for example, or the arithmetic operation. And the sources here means the operand, the operands that you're gonna process, for example, add together so that you're gonna get a new value. So B and C here are our operands. A is operand also, but it's a destination for the arithmetic operations. And there is a note here, okay, that all arithmetic operations have this form. All of them, like add, subtract, whatever, have some, source and destination. And all of them use at most three operands. Okay, and why is this? This because this will reduce, the amount of hardware, or simplify the design of the hardware in your arithmetic logic unit, which is the module inside the processor that do the arithmetics. And here we should introduce to you our first principle of design. Simplicity favors regularity. So if you want to make something simple, make it regular. Unify your world according to that principle or that or make it a pattern, for example. That's why we're gonna unify, or we're gonna make all arithmetic operations have this form, so that one circuit can do, all kind of, or can process all kind of, instructions. So if you have multiple shapes or multiple forms of your arithmetic operations, you must have a circuit to differentiate between the forms. Then and this circuit should, choose one of other circuits to process, because you're gonna have, certain circuits that do this form, another circuits that do this form, and so on. So this will complicate your design. But if you have just one form, then you're gonna have just one, one circuit basically in principle to do this. So regularity makes implementation simpler, as we said. Okay, and also a good implication of that is that this will make your performance faster. So this is a very big rule, or big idea also, in computer architecture, that once you have a simpler circuit, usually this circuit can run faster. So the maximum frequency at which the circuit can operate on, it is really dependent on the complexity of the circuit. Usually, simpler circuits can run at very high speed, and complex circuit, okay, usually run with less maximum speed. So, for example, if you have a circuit that is, for example, 1 millimeter square in area, maybe the maximum frequency that can operate with is 5 gigahertz. If we complicated the design, for example, to make it like 10 millimeter square, 10 times bigger, maybe the higher frequency is 2 or 3, less than 5. Okay, guys? Good. Let's have an example. Let's see, f equal to g plus h minus I plus j. So we have here 5 operands. Okay, so this we have 5 operand. Of course, f is a destination. Okay, and we have here, a more complex, so first we should add g and h, add I and j, then subtract them from each other. But remember, we have one form in our MIPS, add a, b, c. So you have 3 operands. Here we have 5. So what we're gonna do, we're gonna translate this into 3 instructions. So we're gonna first, add g and h and put the result in a register called T0. We're gonna speak about registers, so don't, or consider it as a variable for now. So a variable called T0. Then add I and j and put the result in a variable called T1, and then make the subtraction T0 plus minus T1, so f equal to T0 minus T1. And remember, T0 is G plus H. Remember, T1 is I plus J. Okay? So one instruction in C, for example, or C++, converted to 3 instructions in assembly. Okay? But remember, so you might say, okay, so we have now 3 instructions. So where is the performance gain here? So the performance gain again comes from, the fact is that your circuit becomes simpler, so it can run at higher frequency. So although here you need to do 3 operations, but you can do these 3 operations in a smaller time than, for example, if you have a bigger circuit with much less higher frequency. Good. register operand. So now let's go back and say what is AB, what is IJ, what is this T0 that we saw in the previous example. So that's basically variables, yes, numerical values, but these variables should be stored somewhere. So there should be some, these variables should be so to process some number, this number again will be represented as zeros and ones, and zeros and ones should be stored somewhere so that we can process them. So here is what comes, register, what's called register operands. So arithmetic instructions use register operands and only register operands. And again, once you restrict your instructions to some form and some regulations, again the circuit will be simpler. So we're gonna restrict again our arithmetic instructions to only use register operands. Okay, so these register operands is just like memory spaces, but they are not in the memory. Okay, they are away from the memory. They are still inside the processor, near the arithmetic logic unit. So usually memory is away from the processor, a separate module. So if you have a memory like this, the processor is away from the memory. Okay, it's a separate circuit. So the registers located inside the processor with the ALU, the arithmetic logic unit, the fetch circuit. All we're gonna explore all these modules in our course. So MIPS assumes that there is 32-bit register file. Don't confuse them together. So you have 32 registers. So 0, 1, 2 until 31, from 0 to 31. And each register can hold 32 bits. So you have 32-bit register file. And this is good, if you use these registers, okay, you're gonna constrain or limit the communication with the memory, because using this register may introduce a delay like 10 nanosecond, 20 nanosecond, something like this. But to communicate to the memory, this is between maybe 100 to 150 nanosecond. So it's way slower. That's why we favor always to use the registers, because they are located inside the processor itself, not away like the memory. So the communication delay will be less, much less. So we use these registers for frequently access the data. Again, they are 32 registers, and each one is 32 bits. And usually in architectures, especially MIPS here, this is called word. So if you have a container of data, like a variable of 32 bits, this is a word variable. So each register here can carry a word. Remember, byte is 8 bits, and this is common in all architectures. But the definition of the word, differs from architecture to another architecture. So some architecture defines the word as 16 bits, but MIPS here defines the word as 32 bits. This is really important. But the byte in all architecture is 8 bits. So we will not call these registers 0, 1, 2, 3 until 31. No, we usually, for example, assign them some functions, some jobs that they are specialized to do. So some of them, for example, use for temporary data. Some other use for saved variables. Some others has some other functions that we're gonna cross by in this course, but not now. So for example, you have 10 of them for temporary data values from T0 to T1, T9, I'm sorry. And for saved variables, registers S0 until S7. And the dollar sign here means the register. So this is just, to say this is register. Another principle here, design principle 2, smaller is faster. this is what I mentioned in the first one, you know. So, but this is very clear here with the registers. So now why, you know, accessing registers is faster than accessing the memory? And because registers are just 32 ones. 32, we have only 32 registers, and they are located, you know, inside the processor, because they are just 32 you know, registers. So they are smaller numbers. So I can locate them inside the, you know, or near the ALU. But the memory, for example, is 1 mega, right? You know, it's really big. So I can't locate it inside the processor. It must be away from the processor. So, and usually accessing, you know, memory, you know, the delay to access the memory is proportional to the size of the memory. So the delay, the memory access delay is proportional to the memory size. So we can say, for example, this is just a made up example. Like if you have a memory of 1 megabyte, then the access delay to read 1 byte, for example, is, let's say, you know, 100 nanosecond. If it's 2 megabyte, maybe the access delay will be, you know, 300 or 250. Okay, so whenever you increase, you know, the memory size, you will increase the access delay, and also power, by the way. But let's now concentrate for the delay. Now, the second question that might arise to your mind: why there are not 64 registers or 50 registers, something bigger than 52? So this is a design choice. Again, if you increase the number of registers, you know, you're gonna have, you know, higher delay to access them. So it's not also, you know, and also have a hard time as a designer to put them near the processor, near the ALU. So they will be a little bit farther, and once you have a little bit farther registers, the access time will be higher, and so on. So that's why we choose some number and stick to it. If you choose higher number, you're gonna have higher delay. If you choose less number, you know, you're gonna have less delay, but at the same time, your flexibility to you know, or your probability to access the memory will be higher, because now, for example, if you have 32 registers and you have, for example, 32 variables, you can use all the registers. That you cannot, you can just avoid using the memory. But if you have 16 registers, okay, yes, accessing registers will be less in delay, like for example from 10 nanosecond to 1 nanosecond. But now, if you have 32 variables, 16 of them must be in the memory. And to access these 16 variables, you're going to have, for example, like 100 nanosecond to access one of them. So it's a trade-off. More registers means less memory access, which is good. But also means, which is the bad side, you know, hard time to design and to locate these registers inside, you know, the processor or near the ALU. Now let's see an example. So this is basically the exact example that we saw before, but now this was real MIPS. So for example, we said that, you know, T0 here is equal to G plus H, which is not correct, because we don't have the concept of variables like in C or C++. Everything here should be in a register. So we're gonna assume here that register S1 has the value of G, register S2 has the value of H. So here, register T0 will be equal to the value of inside S1 plus the value inside S2. Same for T1, it will be equal to the value inside S3, which is I, in that case, assuming it's I, and the value of S4. Of course, there are preceding, you know, code here that we didn't write, in which we move the value of G inside, which is basically in the memory, inside S1 and move the value of H inside S2 and so on. And finally, here, S0 will be equal to T0 minus register T1. That's MIPS. Okay, the other one was just, a preliminary example. It's close to MIPS, but not completely MIPS. Memory operand. So now the hidden part that we didn't. So I said that there are some hidden in the previous example. There are some hidden codes that I didn't show you, in which we move the value of G, the variable G, from the memory to, for example, S1, for example, like yes, S1, and of course for H and I and J. Okay, so basically, there might be some values, for variables inside the memory. For example, if you have 32 registers, but you have 50 variables in your program, so for sure, some of them will be in the memory. At least 18, one of them will be in the memory. Okay. Also, memory, will hold the composite variable, complex variables, like for example, arrays, or structure, or dynamic data. Dynamic data that doesn't have a fixed size. Like for example, you define an array that doesn't have fixed size, and you, for example, you fill this array on demand based on the program behavior or the application behavior. So this, of course, will not, like, for if you have an array of 1,000 element, of course, you must use the memory, not the registers. You have only 32 registers. So to apply arithmetic operations on these complex, data types or variables, you must first load, these variables from the memory to the registers, and then apply or do your arithmetic, because again, arithmetic instructions only use registers. This is to simplify the design again. Okay, and then once you finish this, you're gonna store back the result in the memory. If of course, if this is if this is required. So if you have a processor like this and you have a memory like this, first you load some values in the memory into some registers, and you do your arithmetic on the register, and then store back the final result into the memory again if this is required. I mean, if the final variable is recorded in the memory, not in some register. Let's talk a little bit about our memory here. Our memory is byte addressed. That means you can imagine the memory like this. Have locations like this, and each location is 1 byte. So 8 bits, 1 byte. So the width here is 1 byte or 8 bits. That's what's meant by, byte addressed. So each address is pointing to one location, and this location is 1 byte. How about if you have a variable, and this variable, have a value that cannot be contained in 1 byte, like if a variable in your C, for example, program is equal to like 256. 256 is 9 bits. It's 100000000, because 256 is 2 to the power of 8. So this is 2 to the power of 0, 1, 2, 3, 4, 5, 6, 7, 8. This is 2 to the power of 8. This is 9 bits. So 1 byte here is not enough. So in that case, the variable will be located, will be divided into multiple bytes. But your circuit will when it comes to deal with such variables, will transfer all the locations at the same time. So don't worry about that. Also, we should know how we're gonna store this multiple byte variables in the memory. Okay, so let's say you have this. Let's talk about this example. A is equal to 256. Okay, so this needs 2 bytes at least. So let's say this will be stored in the first location in the memory. So this location, for example, if you have, for example, let's say 250, 256 locations. So you're gonna start from location 0 in hexadecimal to location FF. So you're gonna start by storing here 8 zeros, okay? And then the 1 will be here. And of course, the 1, if you convert it into binary, it will be something like this. Okay? But this is not the case because this is called Little Indian. Little Indian. Okay? In Little Indian, you put the least significant byte in the lower address and the most significant byte in the higher address. So the lower address here is 00, the one next is 01. Of course, in hexadecimal. In Big Indian, you're gonna put the 1 here and the 0 here. Of course, it's very small here, but let's make it bigger. So let's say this is, and here is, so this is Big Indian, Big Indian, and the MIPS is Big Indian. Some other architectures, like for example, like x86 or Intel processors, is Little Indian. Okay, but here we are Big Indian. Big Indian means the most significant byte is located at the least address of a word. Here, of course, we have, it's not a word, it's just a 2 byte, but same concept. If you have a variable that is, this variable is 4 byte, again, the most significant byte will be the one at the least address. And Little Indian is the opposite. Let's have an example. Let's say you have an array. This array is called A. And you have 2 variables G and H, and you wanna, add the variable of A at location 8 to H and assign the value to the result to a variable called G. Let's assume the value G is in register S1. The value of H is in register S2. And the base address of A in register S3. What does that mean? So let's assume that A is is like let's say uh, 10 values. Okay, so you have 10 elements in that array. Okay, so each element is 4 bytes. So that's basically A of 0. And then another 4 byte for A of 1. And then another 4 byte for A of 2. And so on. Okay. Of course, we don't need to store all the addresses of all the locations in A because they are all related and they are all neighbors to each other. So what we need to do here is to store the address of the first location only, the first byte even of the first location, which is A of 0 here. Okay, then we can relate to that location based on the based on the elements that we want to read. For example, if you want to read if you want to read a of 0, so that's basically will be S3. If you want to read a of 1, this will be S3 plus how much? Plus 4. If you want to read a of 2, this is for a of 1. a of 2 is located at the address at S3 plus 8 and so on. So there is a pattern here. So a of 0 is located at S3 plus 0. Of course, plus 0 is just, but I want to show you the relation. Then you add 1 here, you have 4 here. Add 2 here, you have 8 here. So basically, to read a of 8, this will be 8 multiplied by 4, 32. How to write this? So first, to do this, as we said, we should load first a of 8 into some register and then do the addition. So we're gonna load word. L means load, and the W means word. 4 bytes. Load to what? To register T0. Load from where? We should load A of 8. A of 8 is the first location in array A is in S3, and we should add 32 to this. 8 multiplied by 4. 8 multiplied by 4 equal to 32. And once you have, the value of A of 8 in T0, you can do the addition. Another example. What if the destination is array is another another element in the array A, another location basically. Here we should do load and store, because again, the add instruction, the arithmetic instruction in general cannot go directly and process data in the memory in MIPS instruction set. So first we should load A of 8 to a register, do the arithmetic only on a registers, and then store back the result into A of 12. Okay, so first we load, just like the first example, S3 plus 32, because 8 multiplied by 4 will give you 32. After we load the value of A of 8 into T0, we add to T0 to H. H is located in S2, and we put, the result again in T0. That's okay. So we save some register here. Okay, instead of using another register, we save one. And then we store back the value of T0 in A of 12. A of 12 located at the address S3, which is the location of the first byte in the array A, plus 48. 48 is 12 multiplied by 4. Good. Now, just, a concluding remarks here. Using registers versus using the memory. Using we said this, during our talk or discussion, but let's concentrate more on them. So again, registers are faster to access the memory. Why? Small set, very close to the processor. Okay, memory big, far from the processor. Operating on memory data requires load and store, because MIPS arithmetic instructions cannot directly manipulate data in the memory. So we first load, process and register, store back to the memory. That might look a bit complication, but again, this makes the design of the processor, simpler and faster. That's good, not bad. Compiler must use registers for variables as much as possible. Why? Because accessing registers is much faster than accessing the memory. So the compiler, which converts your high-level language into into machine code, and the machine code again has or assembly has two or the machine code has two forms, binary form, not human readable, and the assembly form which is human readable. So these compilers must or try their best to use as much as register as possible. Why? Because accessing register is much faster than accessing memory. One way to do this is to locate the variables that are less frequently used and store them in the memory. That's one technique. Also, register optimization, meaning try to let's explain this in this example here. So in that example, after we load the value of a of 8 into 20, we could here use, for example, T1, but now you are using two registers, T0 and T1. While after this operation, you don't need the old, you don't need a of 8 anymore. So that's why we use the again a of 8 to store the value that will go to a of 12. That's register optimization is important. Finally, we're gonna talk about immediate operands. Immediate operands, is basically constants. Let's say all what we explained so far, something like this: a is equal to x plus y. Okay, so we have three operands here. But how about if you have an operation like this: a is equal to x plus 1. So you have a constant operand here. It's called the immediate operand. Okay, so immediate operand is a constant and usually appears a lot in our programs. So if they appear a lot in our programs, we should also optimize or create circuits to deal with them in a simpler way again. So for that case, you have a principle, a third principle of design: make the common case faster. So small constants are very common, as I said. Okay, it appears 50%, for example, in spec benchmark. Spec is a kind of programs that we use to check the speed of processors. So when we translate spec, we find that most of the time, or half of the time basically, is use immediate operands. So if you have an immediate operand, then you don't need to load it from the memory, because it will not change. Memory used for variables that will change over time. You might change it, at least over time. But constant operand doesn't change. It's one all the time. So for that reason, we should we should care about this case in our design of the hardware, so that this case is processed faster. And that's why we have what's called add immediate, in which, for example, here S3 equal to S3 plus 4. Okay, so you don't need to load this 4 from the memory, for example, or store it in a register. You don't need to do so. And even for subtraction, since this operand can be negative, if you want to say S3 equal to S3 minus 4, just make the addition again, but make it minus 4 or minus 1 in that case, for example. Finally, many times we need to to move or copy from register to another register. In x86 Intel processors, there is an instruction called move that do this. But how about if you add a equal to b plus 0? What's going to happen here? Since b plus 0 is b, that's basically copying b into a, right? So you don't have to do you know, another circuit that do the move. The addition circuit can be used for this. Okay, so to do the move, we use, you know, like add, you know, the first register, the second register. This is the destination. This is the source. This is like A. This is like B. And you can say 0 or register 0. So there is a register. This register is made specifically to that operation, the move operation. So instead of defining, you know, 0 immediate variable, if the immediate constant, you can use this register. This register has 0 all the time. So that by this, we don't create another circuit to do the move. We just use the same circuit that do the, you know, the addition, which is really great. You save area, you make you know, your, and this will of course will, you know, will simplify the design of your processor. That's it, guys, for this you know, for this lecture. Thank you very much, and see you in the next video. Bye.